And again, back to that study on national mean gas price on particularly that date, June 1st, 2020. We still haven't found the population mean. And at given sample size here, given sample size n equals 36, we realize that we can have not only one sample mean. So our first sample was $1.69, but now we realize that we can have not only one sample, but we can have many other ones. So I named them X bar 1 coming out from sample 1, X bar 2 coming out from sample 2, and X bar 3 as a sample mean that came out from sample 3, and we can have many more. And then further we realize that any of these came out from and we generally regard any of these as a sampling distribution or a population of sample means. And I use the subscript 36 here next to my random variable capital X bar. So now the main point here is that we realize there are infinitely many values provided that we are in the same sample size throughout all of these samples. So the question now is, can we average? Can we average, or basically finding the mean of these X bars right here? These X bar I already had, and many more waiting. Can we average them? And if we average them, what kind of value do we expect here? And that's where we're heading. And generally, I'm talking about in any sampling distribution of a mean at a given sample size in each sample over here. Then we have in that sampling distribution, we have X bar 1, X bar 2, X bar 3. I'll never be able to write enough all of those sample means out there, but the question now is, can we average all of these? Can all these sample means, X bars, a lot of them, infinitely many of them, can all these X bars be averaged? So back to that question, can we average all of these sample means of gas prices? Yes, we can. The answer is yes, we can. And so if we were to find that average of all these sample means, so now keep in mind, I'm not averaging single gas prices. I'm not talking about the population mean of gas price. I'm not talking about the national mean gas price. I'm talking about now obtaining the mean of after averaging all of these sample means value. Then if we were about to find that, how would that happen? Well, X bar 1 is one of our values. So $1.69 as a sample mean. I am going to add to my next one $1.72 as another sample mean in my sample 2, and add to my third value as a sample means in my sample 3, and I have many more waiting. So namely X bar 4 plus X bar 5 and so on. And here I'm gonna have to really leave dots here because I don't know how many more are waiting for us. And just the same way of how we're finding the average. Anytime we're finding the average, the mean value here, it's the mean value on all the sample means. Then we need to add all the sample means value that we currently have as our data and divide by, really, we know there has to be eventually an ending number for how big, how many sample means we have here, but really at this point nobody knows how many more sample means are waiting for us out there in the entire population of sample means. So here all I can say is we are going to, after adding up all the sample means, then we are going to divide by all there are. Meaning if you can have millions of these sample means, we really are going to divide by all of those. We refer to this average of all the sample means here. Now realize again that this is a population of sample mean values. So this means that we're attempting to get here must be a mu, population mean. But now, since each value here is being a sample means value in particular, not a single price, so I'm going to start using this symbol. It's a mu for population mean of all the sample means. So it's a mu with a subscript x bar. So mu with subscript x bar from now on means it's a population mean. It's a mean value, a population mean on any sampling distribution where data values are being sample means. So again, generally speaking, for any sampling distributions, basically indicating we have a population of sample means where there are n values in each sample. This is the sample size at a given sample size. So this mean value come out. This sample mean come out from n values. This other sample mean come out from another n values. This sample mean also comes out from an n values. So we are going to have infinitely many sample means. The question I addressed generally earlier, can all of these sample means be averaged? Yes, they can. They can be averaged. So how do we average them? We find whatever we call that our first sample mean we are going to add today to our next sample mean. It's just the only way of finding mean value. We have to add up all values in the data and divide by all they are, plus our third sample mean, and I do not know how many more sample means to be added into our sum here, so I'm leaving dots there. And after adding all, theoretically adding all sample mean values existing in our sampling distribution, then we are going to divide by the number of all sample means there are. I'm not saying that this number is small, and as a matter of fact at this point, and I will never know what this number is, but in theory it exists. We call this mean, and like I said again, capital X bar with a subscript n. After many times I explained this is a population of sample means provided each sample here are in the same sample size. So averaging all of these sample means here, what we have here is intended to be a population mean, but population mean of sample means. So that's how we find mu x bar. So mu x bar in theory at this starting point right now is basically the average out of all sample means. So now as the bottom line, let capital X bar sub n represents a distribution of sample mean or a sampling distribution of sample means, or in other words, a population of sample means. Then in that way, mu x bar is the mean of the population. Sample means. And again, I need to remind everyone who's viewing this video that anytime we're looking for mean of a population or the mean of a data, the reason mean is so important to find because mean is the center of the data. So here mu x bar in our case here is the center of the population. X bars. It's the center tells anyone who reads the data a sense about where this population of sample means focus at. That's why mean value in any data set is so important, because it tells where the center of the data is. And so we've learned from the beginning of our quarter that anytime after we found the center of a population or the center of a data, so here our data is being a population of sample means, but generally after we found out where the center of a data is, then the next thing we do now is to look for a standard deviation, a sigma. So sigma x bar, in this case, once again, back to our sampling distribution of the sample means here, or our population, what we have here is a population of sample means. Then after we recognize center of the population, of this current population of sample means, generally regarded as a mu sub x bar, then sigma by itself is this population standard deviation, is the standard deviation of this population. And since our population is the population where data is being sample mean, so I'm introducing that subscript, I'm introducing that symbol being sigma subscript x bar. So sigma subscript x bar associated with this sampling distribution, capital X bar sub n right here, is the standard deviation. Of all sample means together. But once again, what's important about a standard deviation is that any standard deviation, being a sample standard deviation or being a population standard deviation, is indicating is the average spreading or in short, it's just the spreading of the data, the average spreading of the population or of the data values. Of X bars, or average spreading, how members being spread away from the center. And that is why anytime for any data that we're looking at, once we found a mean, the next step is to find standard deviation, how on average, how data values being spread away from the center. And so now, before we get too far, allow me to clearly distinguish between mu x bar and mu right here. So clearly speaking, mu x bar is not mu, because at this point of our learning here in statistics, then we have seen a lot of symbols, and sometimes due to so much similarities between symbols, then it's easy to confuse. So I have to make clear that mu x bar, it's a mean. Mu is also a population mean. Mu x bar is a population mean, but they are not the same thing. They are two different objects. Mu x bar is not mu. Similarly, sigma x bar that we've just learned is not any usual sigma. And here's the reason why I had to make such clear distinguishment. Allow me to recall that question about national mean gas price on June 1st, 2020 again. So the answer to this question was intended to be that population mean mu right here. But so now we must understand that this population mean, and it's just the plain, traditional, plain old mu right here, no x bar subscript. Some part of the video we talked about the difference between a plain capital letter X to represent a single individual, single value versus capital X bar with a subscript. And so here, this national mean gas price, if we're looking at every individual gas price throughout the entire nation, then the plain capital X is the value of a gas price. It could be a gas price right in some corner of in the street in Seattle, Washington. It could be a gas price on some gas station at the corner of the street in Chicago, Illinois, things like that. And so this is a population of data, but population of single gas prices, individual gas prices. And so the population mean there is a mu, as well as the standard deviation there, average spreading on that population, is a sigma, the plain traditional sigma. We already also learned that we were attempting to find the answer to this question. We couldn't. So up until this point, the true population mean gas price on that day, on that date, is still a mystery. But what we found is that we found sample x bar 1 being 1.69 according to our first sample. Sample 2 had a sample mean $1.72, and our sample 3 was $1.68. And from this study and observing that we can end up with infinitely many sample means like this, we came to our previous conclusion that what we have here is a sampling distribution of sample means, or a population of sample means, because there are many more waiting for us. And so, and all of these samples all have the same sample size, equal sample size, being 36 prices in each of these samples to come up with the sample means. And so we regard to this as a capital X bar 36 in our learning previously. So I explained earlier that capital X bar 36 represents the value, or the mean gas price of a sample of 36 prices. So any of these, so any value that capital X bar 36 equals to, it's a mean of gas price, but of 36 sample prices, 36 prices together. But since we have many of these sample means, as I just pointed out and erased, then this sampling distribution of sample means has the population mean there being the mu x bar, and the standard deviation on that population of sample means is the sigma x bar. So clearly speaking, the reason I put a column separator here is that these are completely two separate populations. This is the center of this corresponding population, whereas the mu x bar is the center to this population. So they are different things. They come from two different populations, two different families. And the same with the two population standard deviation here. Sigma, the traditional plain old sigma here is the average spread on this population of single individual gas prices, whereas sigma x bar here is the population standard deviation of the sample means gas price population. And so to make it convenient for communication, then a lot of time many textbooks and statisticians refer to sigma x bar as a name to make it a little bit different, to clearly indicate that there are different population standard deviation. They come from two different populations. So sigma x bar from now on has a name, a lot of time being referred as the standard error. But truly speaking, this is the population standard deviation on the population of sample means, and versus just the population standard deviation. So the traditional sigma here is just simply the standard deviation. And this is now the last thing I would like to show everybody who views this video. before we ending our lecture on sampling distributions of the mean value. So on my computer screen here, let's say I'm starting out with sample size being 20 in each sample. So the rule we're doing here, let's set our goal here is to have 20 gas prices in each sample. The plan is we are going to collect 100 sample mean values. So for now, 100 sample means values are going to be collected, where each sample is a sample of 20 gas prices. On my computer screen here, I am going to be using my simulator. So the first sample we found here, so if everybody is looking closely, then this is a sample where it has 20 gas prices collected nationwide. Back on, and as a reminder again, this is the gas prices collected on June 1st, 2020. So in this first sample, the sample mean we found here is $1.54. And anyone who viewed this video can disregard about the standard deviation. This is a sample. Standard deviation is only applicable to this sample. We don't need to worry about that. But so we have a sample size being 20, and the sample mean value came out from this sample is $1.54. And so we can regard to that as x bar 1 equals 1.54. So this is our first sample mean value. I am going to record this mean value into my Microsoft Excel. And so here I'm preparing 3 columns. So for sample size being 20, and later on after this activity, I'm going to do another one for sample size 36 and sample size 100. But for now, we are looking at sample size being 20 in each sample. So first sample I found is being $1.54. So that sample mean is being recorded there. And I am going to back to my simulator. I am going to run again, where it's going to select a different sample. And so I am going to refresh this simulator, and it's going to come up for me a different sample. So anyone viewing this video now can realize that here we are at a different sample, another sample of 20 gas prices individually selected nationwide on June 1st, 2020. And the sample mean came out this time is $1.57. And so back into my Microsoft Excel, I am going to record that value being $1.57. And again, I am going to run another sample collection here. And my third sample is being $1.56. And again, this is a completely different sample, 20 prices, individual prices in my sample. And the sample mean came out in this third sample is $1.56. And so now $1.56 is being recorded in my Microsoft Excel under the column for n equals 20. And then another sample. So now in my fourth sample here, again, there are 20 gas prices, and the sample mean value from that sample came out to be $1.77. And once again, $1.77 is being recorded in my Microsoft Excel under that column for n equals 20. So to not waste your time viewing the video, I will speed up the process here. So basically, I will repeat the exact sample collecting work here for another 96 samples, because my aim here is to have about a collection of 100 sample means here. All right, so now after successfully collecting 100 samples where 20 gas prices are being contained in each sample, then this is my complete collection. So what I have here now is 100 sample means where each sample mean here came out from a sample of 20 individual gas prices. So of course 100 sample means is not enough to be a population. However, we are trying to pretend that what we came up here is a sampling distribution of the mean where the sample size is being 20 in each of my sample. And so once again, capital X bar here represents the mean price of a sample of 20 prices. So if we really spent time to find all samples out there to come up with all existing sample means of capital X bar 20, then we would end up with a lot more sample mean values than this. However, here 100 sample means, it's enough to describe the behavior of capital X bar 20 that I'm about to show. So as a bottom line, 100 sample means in this column represents the population of sample means where each sample has 20 gas prices. And after collecting 100 sample means of gas prices where sample size is being 20, now I'm going to repeat the activity here where I'm going to set my goal for another 100 sample means of gas prices, but this time I am going to aim at sample size being 36 gas prices. So meaning each of my sample means that I'm going to collect is going to be an average of 36 individual prices. And so now once again my software simulator here is ready for this work. Our first sample here is being, and anyone viewing this video can quickly count that there are 36 individual prizes collect nationwide on June 1st, 2020. And so being the first sample, I call this X bar 1, but this is $1.71. So our first sample. And this first sample is going to be recorded into my Microsoft Excel column. And so now we're looking at $1.71 being recorded into Microsoft Excel under that column with sample size being 36. Then I'm going to get another sample. So I'm going to run my simulator again. So running my simulator again, it collects for me a different sample where 36 prizes are contained in this sample. That's why sample size being 36. But here my sample mean came out differently. X bar equals $1.68. So we can call this an X bar 2 right here, $1.68. And so just like any of us at this point have been well aware that we cannot really expect any sample to be the same as any other sample. It could turn out equal value as a sample mean, but every sample is a different sample. And so this sample mean number 2 right here is going to be recorded. So $1.68 recorded into my Microsoft Excel column. And once again, I'm going to start speeding up the process here. And so here we are again. I am now finished searching for another 100 sample means, where each sample mean here came out from a sample of 36 prizes nationwide. And once again, my plan here is I am going to treat this, even though there are only 100 sample means, which is not anywhere enough to be a sampling distribution. However, this should be behaving similarly to an actual sampling means sampling distribution. But so this column here is representing my capital X bar 36. This is going to be each value of my capital X bar 36 represents the mean price of a sample of this time 36 gas prices. And now I am going to repeat the activity one more time, but this time each sample of mine is going to contain 100 individual gas prices, or in other words, now I am going to switch to sample size being n equals 100. So same goal, I am going to collect 100 sample means, and each of my sample has a sample size 100. So on my simulator again, here's our first sample. X bar 1 is $1.71, where sample size being 100. And so anyone viewing this video can now well realize that we have a lot more, and each one of these data value here is an individual price collected nationwide on June 1st, 2020. And so this is a sample of 100 individual gas prices, and the sample mean came out being $1.71. And then I am going to record this sample mean into my column in the Microsoft Excel spreadsheet, where I'm at the column for n equals 100. So 1.71 is being recorded there. And again, I am going to run my simulator quite a few more times. So again, for a different sample of 100 prices, so 100 individual prices being collected here, my sample mean came out again $1.71. So X bar 2 came out $1.71, and I am going to record again $1.71 being recorded into my column on the Microsoft Excel spreadsheet for n equals 100. And the third sample, here we go. So here's in my third sample, 100 gas prices. The sample mean this time came out $1.77, not too far from the two previous samples. So the third sample is once again being recorded into my Microsoft Excel spreadsheet. And here we are at my fourth sample. And my fourth sample, another 100 gas prices individually collected nationwide on June 1st, 2020. Then the sample mean that came out from this sample was $1.70. And this fourth sample mean is now going to be recorded. And once again, I am going to speed up the process. And our goal again is to obtain 100 sample means here, where each sample is containing 100 prices. So here we are. This is another 100 sample means of mine right here, where each sample came out from 100 gas price, or sample size 100. So I gotta make it clear again that none of these is close enough. None of these collection of sample means is enough to be a sampling distribution of the means. However, whatever I'm about to do after this is going to behave similarly to a real sampling distribution of the mean. But once again, for this third column, any of these or this collection I've made right here is part of the capital X bar with subscript 100. According to my style for naming the random variable to represent a distribution of sample mean, then each value of a capital X bar 100 represents the mean price of a sample of 100 gas prices. And of course, everything we're doing here is still circulating around that gas price research, that gas price collection work we did back on June 1st, 2020. And now, after successfully collecting 100 sample means for each sample size, so here respectively I've had sample size equals 20, sample size equals 36, and sample size equals 100. So here for 100 sample means coming out from sample size 20, this is what I've created here. I arranged all these sample means into a histogram. So similar to what we have learned way in the beginning of our quarter. And so the histogram of this 100 sample means, where sample size being 20, appears to be as the following. And once again, I have to make clear that only having 100 sample means is nowhere enough to represent an actual sampling distribution of the mean. However, what I would like, the point I would like to say now is that even though with the sample size being small, capital X bar 20, and remind yourself that capital X bar 20 is to represent the mean of a sample of 20 gas prices. But this sampling distribution of the mean, the point I'm trying to say now is that it will have a distribution shape. And so only 100 sample means will not be enough, but think about once you have made, collected all sample means of size 20 on each right there, then we have some kind of distribution. And so the picture currently showing me in my histogram here currently only based out on 100 sample mean values, we already had a distribution shape that kind of looking two peaks like this. And so let's look over to the other sampling distribution. Now when I change to sample size being 36 right here, then here's my histogram describing my first 100 sample means that I have collected. But so once again, currently we are representing our capital X bar 36, where each value of this random variable is the mean price of a sample of 36 gas prices. So we increased the number of gas prices in each of our sample. And look at the histogram again. But so we don't need to be worried about how to build a histogram. You've learned all that skills back in the beginning of our quarter. But the point I would like to show here is that we are looking at a distribution shape. So once again, once we can reach all sample means where 36 prices in each sample, then this sampling distribution of our mean here will be carrying a slightly different shape. It looks like this time it's becoming a one peak thing now. So unlike capital X bar 20, now capital X bar 36 turn into a one peak distribution shape. And now turning our focus to the last collection of our sample means here. So in my last column here, this is 100 sample means, where each sample mean came out from a sample of 100 gas prices. Then the histogram looks as following. So here's my histogram, and once again, what I'm trying to describe is the behavior on my sampling distribution of the means, where 100 prices is being in each sample, or sample size is 100. So once again, very similar meanings. Capital X bar 100 is the mean price of a sample of 100 gas prices. And so what I notice here is once again, if we can arrange, having currently only 100 sample means to be placed in a histogram is nowhere enough to an actual sampling distribution of the means. But if we can achieve, if we can reach all sample means where each sample is 100 in size, then our histogram would definitely turn out into another peak thing right here. One peak only, and yes, this is another distribution shape. My point I would like to show anybody is that, so for any sampling distribution of the mean where sample size is capital letter N, we already understood that the symbol, what the symbol mu x bar represents, and the symbol sigma x bar is to represent. Brief reminder, this represents the center of this current sampling distribution, and this is the average spreading. So how sample mean values are being spread away from the center that we calculated. So this is average spreading. But besides the information, the understanding about center and average spreading, any sampling distribution of the mean, has a distribution shape. So that's the third property that we would like to investigate, and that's my whole entire purpose of coming up with 3 different sampling distributions to show everybody the histograms. And so the distribution on any sampling distribution can be either a multiple peak like you've seen in the first case, or it could be down to only one peak, but possibly be either skewed right or skewed left. Or it could all focused to become a one nice symmetric peak, as we have seen in a normal distribution. So in the lectures after this video lesson, we are going to get further into studying what factor decides the distribution shape, as well as how we can completely calculate the precise value of the center and average spreading on any sampling distribution. And so these 3 main factors, how we can calculate center, how we can calculate average spreading on any distribution, on any sampling distribution, as well as how we can decide what distribution shape any of our sampling distribution is going to become, that will come in our following video lessons. The point is, we can bypass constructing histogram, but we can immediately decide whether our sampling distribution shape can become a normal distribution or not.